Good morning everyone, and welcome to today's worked exam answer question. Today I'm back with another of everyone's favourite question, which is a time of flight mass spectrometry calculation question. And this, in my opinion, is one of the hardest, and I say hardest, it's one of the most time consuming versions of this type of question that you can get. So this question is taken from an AQA paper. Can't remember if it's an AS paper or an A-level paper, but this is one of the year 12 topics that they will frequently put on the A-level papers because they know that students are not massively fond of time of flight calculations. So it very much could appear on both an AS or an A-level AQA paper. The reason why I think this is particularly time consuming is because we're not just thinking about one isotope of an element in this question. We are dealing with bromine, and we are told that bromine is found to contain two isotopes, 79 bromine and 81 bromine. Now we're then given information about the 79 bromine, but ultimately asked to find something out about the 81 bromine. Now, it does remind us here of the key thing that we need to, know for this question, which is after we have ionized both of the bromine atoms into ions, they will be both accelerated to the same kinetic energy. And that is key here, because what we're going to need to do is use the information that we've been given about the 79 bromine isotope to work out the kinetic energy, and then knowing that the kinetic energy for both ions will be the same, we can then use the kinetic energy and the information that we've already been given to figure out the time it takes for the 81 bromide ions to move down the flight tube. So I'm going to kind of break this up into two halves, do what we need to do with the 79 bromine isotope here, what we then need to do with the bromine 81 isotope on this side. And then there's two kind of things that you're going to get kind of specific marks for on the line. One is the mass of one ion of the 79 bromine isotope in kilograms, and that's one of the key things that we need to remember about these types of calculations, is that mass everywhere else want it in grams, here you want it in kilograms. Then the second thing that we're trying to find out is the time taken by the 81 bromine ions. So let's go back to the start and read through the whole question together. I am going to pick out things that only belong to either the 79 or 81 bromine isotopes, and then I should probably have a third colour for the things that refer to both ions. Okay. So, a sample of bromine was analysed in a time of flight mass spectrometer and found to contain two isotopes. So we've got everything to do with the 79 bromine in the light blue and everything to do with the 81 bromine in the dark blue. Then it says, after electron impact ionization, all of the ions were accelerated to the same kinetic energy. So we've got pink for everything that applies to both. And then the ions travelled through a flight tube that was 0.95 metres long. So both ions will be travelling through the same flight tube and covering the same distance. Okay. We're then told that the 79 Br plus ions took 6.69 times 10 to the minus 4 seconds to travel through the flight tube. And we have to calculate the mass in kilograms of one ion of the 79 Br plus isotope. Then calculate the time taken for the 81 Br plus ions to travel through the same flight tube. Again, relevant for both ions is the Avogadro's constant, 6.022 times 10 to the power 23 moles to the -1. And then they've actually given us 2 of the 3 equations we're going to need here. The kinetic energy equation, which is the one they usually give us, and they will remind us that mass should be in kilograms and that speed or velocity is in meters per second. Length of the flight tube's been given in meters, so we don't need to do anything with regards to converting that. And then they've also given us here the speed or velocity is distance over time equation, where distance is in meters and time is in seconds. And again, distance in meters, time for the 79 ion we've been given in seconds. So the one equation that they haven't given us here is the way in which we're going to calculate the mass of these ions using moles and MR, except it's not going to be MR, it's going to be mass number, and it's not going to be kind of moles in that we're given the moles. We're going to have to work out the moles by using Avogadro's constant, and that's the one that they haven't given us. So here we go. The 79 BR plus calculations that we need to do are as follows. So we need to calculate the mass in kilograms of 1 ion of that. So mass, as I've said, normally equal to moles times MR. Now, moles can also be worked out by doing number of particles divided by Avogadro's constant. And the number of particles, it says we're calculating the mass of 1 ion. So the number of particles is 1. Avogadro's constant is 6.022 times 10 to the power of 23. And that's going to be used for our moles. And then the MR, it's not going to be MR, it's going to be mass number of this particular bromine isotope, which is 79. Now that will give me the mass in grams, which comes out as 1.31 times 10 to the -22 grams to 3 significant figures. So then I'm just going to divide that by 1,000 to get it into kilograms, which is going to be 1.31 times 10 to the power of -25 kilograms. So from there to there, we're just dividing by 1,000. That is then the mass of 1 ion of the 79 Br plus. So that can then go straight onto there, and we will get marks, even if you're not sure how to do any of the rest of the question, so long as you know how to calculate the mass using that mass, moles and MR kind of variation of that equation, then you'll pick up some of the marks here. Now, in order for us to do anything with the 81 Br plus isotope, we need the kinetic energy. So again, we can work out the mass of the 81 ions by doing exactly the same thing. We've got the length of the flight tube, but unless we have either the velocity or the kinetic energy, we can't go any further, because to get velocity we need distance over time. We don't have the time, that's what we're trying to figure out. So in this equation here, we're trying to work out velocity. We can't work out the velocity unless we have both the mass and the kinetic energy, which we as of yet do not have. However, we can figure out the kinetic energy using the information we now have about the 79 bromine isotope. So kinetic energy is going to be equal to 1/2 times the mass of that ion, which we've just worked out, 1.31 times 10 to the power of -25. And then we're going to be timesing that by the velocity squared. Now, velocity is equal to distance over time. So there's a few ways that you can do this. If you feel comfortable to do this, you can times that by the distance over time squared, or you can just work out velocity separately by doing v equals the distance of 0.950 meters divided by the time taken by the 79 ion to drift through the flight tube, and then figure out what that is and then put that in and square it, which is what I'm going to choose to do here. So 0.95 divided by 6.69 times 10 to the -4 gives me a velocity of 1420.0, and that's going to be in meters per second. So then it's going to be 1420.0 squared. If I figure out what that is on my calculator, I get a value for the kinetic energy of 1.32 to 3 significant figures times 10 to the minus 19. And that kinetic energy will be the same for both ions. Okay, now we're going to go on to the other side, and I've not really left myself massive amount of room here, but never mind. 81 Br plus. So now that we've got the kinetic energy, we can figure out the mass. Once we've got the mass and the kinetic energy, we can rearrange this to get velocity. Once we've got velocity, we can rearrange this, use velocity and distance to get time. Let's go. So exactly the same calculation initially. So the mass of the bromine 81 isotope will again be 1 divided by Avogadro's constant, but this time the mass number is not 79, obviously it's 81. That will again give me the mass in grams. Which is 1.35 times 10 to the minus 22 to 3 significant figures. And again, we're then going to divide that by 1,000 to give me that in kilograms. Then I'm going to rearrange the kinetic energy equation. So velocity is going to be equal to, or initially velocity squared is going to be equal to 2 lots of the kinetic energy divided by the mass. Then we need to square root all of that. So 2 kinetic energy divided by the mass, and that would give me velocity squared, and then we can square root all of that. So we're going to be using this kinetic energy value here in there, and this mass value is going to be the 1.35 times 10 to the minus 25, and that will then give me a velocity of 1,402.4 meters per second. Just gonna make sure it's clear that that value there is the kinetic energy value that we've just found, and that this mass value here is that value there. Because I needed to save myself this little bit of room that I have here to then work out the time. So if velocity is distance over time, time is going to be equal to distance divided by velocity. So the distance is 0.950 meters again. The velocity, as we just worked out, 1,402.4, and that gives me a time of, I'm just going to write it straight on the answer line, 6.774 times 10 to the minus 4. Now before I write that down, I'm going to come back and have a look at how many significant figures are used for the values in the question. So the distance was given to 3 significant figures, the 9, the 5, the 0. Time for the 79 isotope was given to 3 significant figures, the 6, 6, 9. Avogadro is given to 4, but when it comes to quoting our answers, we should always give our answers to the smallest number of significant figures used in the question. We can't be more precise than the least precise bits of data we were given. So we need to go for 3 significant figures, so 6.77 times 10 to the minus 4 seconds for the time taken for the ever so slightly heavier bromine isotope to travel down the exact same flight tube. Now, the good thing about calculations of this nature is because we're dealing with 2 different isotopes with different mass numbers, we can think logically about whether our answer makes sense. So the 79 bromine isotope, which is slightly lighter, took 6.69 times 10 to the minus 4 seconds. The 81 bromine isotope is slightly heavier and took 6.77 times 10 to the minus 4 seconds. So it took slightly longer to travel down the same length of flight tube. Makes sense because it's heavier, it's not going to travel as fast. Same thing for the velocity. The velocity of the lighter ion covered more meters per second than the velocity of the heavier one, which covered less distance per second. Again, that makes sense. If you're doing this question and you end up getting a time for the heavier one, which is smaller than the lighter one, that should be a red flag, an indicator that we've done something potentially wrong. And if you have the time to do so, you can go back through your calculation and try and figure out where you have gone wrong. Hopefully, seeing all of that laid out like that has been useful to some of you. Any questions at all about what I've done here, or the method, or you've got another time of flight calculation that you're looking at and going, I just don't know where to go from here, or I don't know where to start, get in touch with me. You can leave a comment on this video, or you can email me at missg@outlook.com, and I'd be more than willing to help. Thanks so much for watching, guys. Hope you have a brilliant day.